Hi, welcome to the demo session on higher order functions, folds and others. Okay, let's start a GHCA session. We are in VS Code. So let me start GHCA. Okay, started. Let's see if it works properly. 0 plus 3. Let's just test it with some expressions. Okay, so now we looked at higher order functions. One of the first things we looked at was the dollar function. You can see that I can do things like plus 1 applied on 2 plus 2 times 3, let's say 2 times 3 plus 5. Okay, so you will get 17 because it's 2 times 8, which is 16, plus 1 is 17. You could also have written this as plus 1 of dollar applied on you do get an error though. That's because I use dollar within parenthesis. I shouldn't use the parenthesis because I am using it in operator mode. So it's just dollar plus 1 dollar 2 times 3 plus 5 is 17 plus 1 dollar. Let me just check whether I need the parenthesis here also. This also works. Okay, so this is dollar, but now I can use it in function form. Dollar applied on plus 1 and 2 times 3 plus 5. That should also give me 17. Okay, so let's test what the type of dollar is. As you can see, it is a arrow b, which is a function type, which is the first argument it takes, a unary function, and then a value and then the result of applying the function on the value. Okay, so this is about dollar. The thing we looked at next was map. Let's check the type of map. Okay, as you can see, it is a arrow b, arrow list a, arrow list b. So I can do lots of nice things with map x2. Let's check whether square is a function. You can always say colon I to check information about something, colon I or colon info. Square is not a built-in function. Okay, square root is a built-in function. Okay, but we don't need square root. Maybe why not? Let's try applying square root. Okay, map square root on 1 dot dot 10, let's say. Yeah, I get all these values. 1 square root of 2 is 1.41 whatever. Square root of 3 is this. Square root of 4 is 2, and you get all these values. Okay, square root of 9 is 3. Square root of 10 is 3.16. Whatever. Yeah, so this is a very useful function to have. Let's try to program my own map and let's see if it works. My map of f applied on empty list is empty list, whereas my map of f applied on x colon x's equals my map of f of x followed by my map f x's. Let's save this. Let's go here and load the file. And let's do the same thing with my map. Let's see if it works. Yeah, it works, right? So for pretty much one of the nicest ways of learning Haskell is to just go and recreate the definitions of the built-in functions, okay, and that's very nice. Filter, similarly, let's apply filter E1 of 1 dot dot 10. Yeah, I get 2, 4, 6, 8, 10. Map of filter of, let's say map square root filter E1 of 1 dot dot 10. So there is an error. It is not clear what the cause of the error is. Let's try my map and let's see if it works. I get a same error because I did something wrong somewhere, I suppose. Okay, so sometimes GHCI will complain, and all you require to do is to provide a type of whatever result you want. So let's go here and then say that what I want is a list of double as the output. Okay, so there seems to be some issue. Filter E1 1 dot dot 10 gives me 2, 4, 6, 8, 10. Map square root gives me whatever value I want. So we'll figure out why this error happens later. Okay, so another way to do the same thing is, as I said, to do map square root dot filter E1 applied on 1 dot dot 10. Let's say f equals, and let's ask for the type of f. Okay, and this might actually give an error. F applied on 1 dot dot 10, I get an error because for some reason it wants it to be both floating and integral, but if I do it separately it works. So let's move on. So this is map and filter. What else did we do? Yeah, zip and zip width and so on. Let's look at that. Zip of 0 dot dot, let's say, and A to Z, let's say 0 dot dot 100, let's say. Yeah, so you see that I'll get 0A, 1B, 2C, etc. all the way till 25Z, and that's it. Okay, you stop after that, even though the first list is of longer length. Okay, you don't care about that. So that's zip. In the previous demo itself, there is one thing which I forgot to show, which is that if you have these list comprehensions, and if I said xy such that x comes from 1 dot dot 10, y comes from 1 dot dot 10. So here x moves slower. So you fix a value of 1 for x, then run through all values for y, then fix the value of 2 for x and run through all values of y, and so on. If you want it the other way, you just exchange the generators. Now you will fix a value of y and then run through all values of x. Okay. So you have 1 1 2 1 3 1 etc. all the way till 10 1, and then 1 2 3 2 1 2 2 2 etc. Okay. This is just to illustrate what happens with the list comprehension. Okay. So zip width is quite useful. Let's check that. Zip width of okay. So this is, I want to multiply the corresponding elements of 0 dot 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 9 till and 2 dot 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 100, but it will truncate after the first list ends, and you see that you will get 0 21 44 69 96 etc. Okay. So this is zip width, and finally let's look at the two kind of ways in which you do recursion and it being reflected in the folds. Some empty list is 0, right. In this pattern you are making a recursive call and then you are combining the initial value with the result of the recursive call, whereas the other pattern, some prime, let's call it, equals go of 0, where 0 is the accumulator, and where go accumulator empty list is just accumulator, and go accumulator x colon x's is go accumulator plus x of x's. Okay. Here you are repeatedly modifying the accumulator and making the recursive call, whereas you are making a recursive call with the modified accumulator. Here you are combining the first value with the result of the recursive call. Okay. These are the two patterns, and let's both will of course produce the same result. Sum of, let's reload. Okay, so because I should have called it my sum, or let me call it sum 0 sum 1, just to be, because it's confused between the sum that I have defined versus the built-in sum. Let's reload it again. It works. So sum of 1 dot dot 100 should be 5050. Of course, that is the built-in sum. Sum 0 should also be the same. Sum 1 should also be the same. Okay. So now instead we could have just used fold R and fold L. So let's call it sum 2 and sum 3 or not. Sum 2 is just fold R of plus 0. Sum 3 is fold L prime plus 0, but now you will see that it will complain saying that fold L prime is not to be found. Yeah, it says fold L prime is not in scope. So what you need to do is to go up there and on the topmost line say import so import data.list will import all the definitions that are in data.list, but sometimes you might want to just be more selective. So what you do is you just say that I want to just download the definition of fold L prime and not all other things. Okay, so you can specify exactly what you need to import. And let's come here now and do a reload. Ambiguous type it says again. So let's just try to give the type for this function. List int arrow int. And you can give the type for various functions and on all in the same line. So let me just go here and give types for all these functions. If it is all the same type, you can give types for multiple functions on the same line. Okay. So let's hope now it compiles. Let's go here. Let me clear the screen. Let me reload. Now it compiles. Okay. So now I can say sum3 1 dot dot 100 sum4 1 dot dot 100 sum3. I have called it sum0 to sum3. Okay, sum4 is not available, sum2 is available, sum0 to sum3 is what I have called all my functions. Actually, let me go and provide a sum4 which is nothing but just fold L, okay, rather than fold L prime. Actually, let me switch it around. Sum4 is fold L prime, sum3 is fold L. What I want to now do is just to see if there is any difference in performance between fold L and fold L prime. Let's check. Let me reload. Okay, sum3 is what I want to try first because that is fold L. Sum2, let's try 1 dot dot 100,000. Okay, it's fairly quick. One more 0, let's add. Okay, at some point it starts to palpably slow down. Let's use sum3 and see what the corresponding speed is. Sum3 is much slower. Let's now get to sum4 and see what happens. Sum4 is much quicker than sum3, right? See, sum3 took so much time. Sum4 was much quicker. And if you actually add another 0, you might see even more of a difference. Sum4, sum3 for the same number of zeros. Finally you can see that you reached a stage where it is much slower. Okay, maybe it will complete or maybe it will quit midway, saying that, see, stack overflow. Stack overflow is just some term it uses to convey that it has run out of memory, okay, somehow, because it has to carry some huge expressions around and it cannot tackle it, whereas the sum4 version simplifies expression as it goes. So you can see that there is this difference that becomes evident after a point of time. This was a simple function, so it's fine, but in general you can imagine that for much more complex combining functions other than plus, you might see a difference even quicker. Okay, so once again sum3 fails, sum4 for the same number of zeros is reasonably quick. Okay, and it might even be quicker than sum2, I don't know. sum2 remember is the fold R version. Maybe sum2 will also quit saying Stack Overflow, because in fold R also you have to carry some huge expressions around. So if we wait for a while, we might actually get an error message now. So this is just to tell you what the difference is. So it seems like for, see, fold R also fails. So of course this is a contrived example, but you can imagine that there are situations when fold L and fold R will have to carry huge expressions around, whereas fold L prime will be much better. Okay. Let's look at the scan versions since we mentioned it. Partial sums, let me call it, and I want to just give it type listInt arrow listInt. Partial, I want to say rather than partial sums, I will say prefix sums and suffix sums. Prefix sums equals scan L plus 0, suffix sums equals scan R plus 0. And if I go here and if I do a reload, prefix sums of, let's start with a simple example, 1 dot dot 10, I should get 0 for the empty prefix and then 1, 3, 6, 10, etc. Yeah, 0, 1, 3, 6, 10, 15, 21, 28, 36, 45, 45, right? So this is a nice and quick way of getting this, and in general it is not just this thing, prefix sums are useful, right? Because this is just to keep the running total of, you might have some I don't know, so you might have some accounts or whatever, and every day you want a running total, you want the total at the end of each day. Okay, so that is what this represents. Suffix sums, let us look at that for the same 1 dot dot 10. This will start with 55 because that is the largest, yeah, 55, 54, 55 is the sum of 1 plus dot 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 till 10, 54 is the sum of 2 plus whatever till 10, 52 is the sum of 3 plus whatever till 10. So you see that you have to keep subtracting from the left to get the prefix sums, to get the suffix sums. Okay, so finally you have the empty suffix whose sum is 0, right? And the suffix 10 has sum 10, and just to show you, suppose I did suffix sums of reverse of 1 dot dot 10, that's actually the reverse of the prefix sums, right? So I can actually, let me clear the screen. So let me say prefix sums okay, then let me say reverse of suffix sums of reverse of right. So I get 0, 1, 3, 6, the same thing, right? So prefix sums is nothing but reverse of suffix sums of reverse. So I can actually write f equals reverse dot suffix sums dot reverse. Note the type of dot. Yeah, it's BROC arrow, AROB arrow, AROC. Okay, it is just composing two functions, and f applied on 1 dot dot 10 will give you the same result as prefix sums. Okay, so you have this. Okay, so So this is about folds and scans. Okay, so let's now look at that string to num example that we had. So string arrow int is what we want, and since it used this digit to int function, let's import it from data.char. Okay, so then string to num was just fold L of, if I get an n and a c, then I will do 10 times n plus digit to int of c. That is the function, and the initial accumulator value is 0. That's it. So this is my string to num. I'll go and reload it. Fold L, I must say. Fold L prime is even better. Okay, I've reloaded this. So if I say a string to num of I don't know, 3, 5, 6, 7, 8, 9, 1, 0, 3, 5, 2. Okay, I just get the corresponding integer. I can ask for the type of, yeah, of course I need to be careful that I don't, because I mentioned the type to be int rather than integer, I shouldn't just give a long string, then I will get an error, because when you try to do this 10 times accumulator plus n, then it will loop back on itself and there will be an error, right. So, so that's, one needs to be careful about that. Actually, one can have this to be of type integer, but then there is a problem, which is that the digit to int function only converts to int rather than integer. So what you need to do is, you should say to integer of digit to int of c, and then it will work. Let's see if it works by compiling this. Yes, it works, it compiles. So let's now try string to num with a large. Let's just keep typing one. So this is clearly a, yes. So now it works. So now you have a string to num version that works for integers as well. Okay. Okay. So what else did we want to look at? All events. Yeah. So let's yeah. So let's try to download this, load this file where I have more functions written. Week 4 prog, whatever it's called, not reload, load week 4 prog 1.hs. So it says variable not in scope. That's because I don't have fold L prime. I'll try to make this file available for download, so you can download it and play around with this. So yeah, this compiles. Let me clear this. Let's look at what all is there. So you see that I have this MySum version, one which is using folder, another which is using this is the pattern where you make the recursive call and then combine it with the initial value. So here is a naive version of sum length. Here is a version of sum length. Yeah, here is a version of sum length where I use folder again, right. So rather than do sum of map of length ls, I could also do folder f0 where f lx, L is a list, x is a sum of the so you have a list which you have a list of lists. The first list is L, the rest of the lists are L's. So X is the sum of the length of L's, and then you have the list L. What do? You take the length of L and add it to X. That's what you have to do. So that is this function, and actually I can even make it anonymous function. So using a lambda Lx arrow length L plus X. By the way, length L plus X will always be interpreted as taking the length of L and then adding it to X, and not length of L plus X, because there are so-called precedence rules for all these operators. Any named function that you write will always be have the highest precedence, so that will be applied first, and then only all the operators will be applied. Okay, and even among operators there is precedence. If, for instance, if you say 2 plus 3 times 5, you will get 17. Whereas if you want 25, you must actually say 2 plus 3 within parenthesis times 5, right? So star has higher precedence than plus, and any named function has the topmost precedence level. Okay. Okay. So this is various those things. So right. So here is a nice thing. You can actually create a list of functions, right? Because else is a list of numbers 2, 3, 4, 5. F's is a list of functions now. I'm mapping plus to else. So what I will get is 4 functions: the plus 2 function, plus 3 function, plus 4 function, and the plus 5 function. Okay. Of course, I cannot ask it to type. I cannot ask it to print F's, because there is no way to print a function. You can only print a function applied on a value. But now see here what I am doing. I am applying the list of functions on a particular value. So I am applying plus 2, and then plus 3, and then plus 4 and plus 5 on the number 15. So I will get 17, 18, 19, 20. Let's just check what we will get as a result of the x's. L's is 2, 3, 4, 5. X's is 17, 18, 19, 20. See? So you can actually do some fancy things like this. Right now it doesn't seem like there is much use for such a thing, but there are situations when you might actually get to use this. Another way of yeah, that's right. Yeah, now there is this all evens and square evens and so on. So this is map square dot filter even. So square root was a problem, but square evens actually works. Let's just check that square evens. Square evens on 1 dot dot 10. This will actually work. You extract all the even numbers, which is 2, 4, 6, 8, 10, and then you take the squares. That will be 4, 16, 36, 64, and 100. Okay. Okay. So that's about square evens. This capitalize all the vowels we saw. You extract the vowels by filtering the list to see if they are elements of A, E, I, O, U or capital A, E, I, O, U, and then you just map this to upper. Okay. And here I have given my own our own implementations of my filter, my take while, my drop while, etc. Just to see that it works correctly. Look at this my take while, where if px is not, if px is true, then you do x colon my take while px is, otherwise you just stop immediately. Okay. Whereas in filter, if px is true, you include x and then you do filter px's, otherwise you anyway do filter px's. Okay. You don't include x, but you process the rest of the list. Drop while is similar. So drop while, at some point of time you will px will fail, at which point you will just take the entire list x colon x's. Actually a better way to program this would be to say L at, then I don't need to again say x colon x's here, I will just say L. Yeah, I will use at patterns are useful whenever you don't need to repeat the same expression. So this is the point. You shouldn't have to repeat the same expression in your code. So if you are wanting to use some part of the pattern x here and then x's, etc., but also later mention the whole pattern. You better use an at pattern and give it a name, L at x colon xs, and then you are able to refer to L as well as to xs as well as to x in various parts. Okay. So let's check whether my drop while works. Let's check it on some value. My drop while even, let's say, and then I want to do 2 4 dot dot 100 plus plus, here we will also use dollar. See, there are various times when you have to do this plus plus and this 2 4 dot dot 100 plus plus some other list is the whole argument. So I need to put parenthesis. Instead I could just put dollar. That will make whatever comes to the right of the dollar, that will be considered as a single expression as a whole by putting parenthesis around it. And I don't know, let me just say 3 5 or 1 5 dot dot 99 or 101. I'm starting from 1. Okay, 99. Okay, I will get 1 5 dot 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 all the way till no, I wanted to say 1 3. Yeah, so the overall list is, if you look at let's say L equals 2 4 dot dot 100 plus plus 1 3 dot dot 99. If I want the value of L, it is 2 till all the even numbers from 2 to 100 and then all odd numbers from 1 to 99. But if I do my drop while of L, my drop while even L, then all the even numbers will be dropped initially and then you will get the thing. That is because there is no even number later. But suppose I had added, suppose instead I modified my L to become plus plus, let's say 101 to 200. Okay. So now if I say my take while even L, it will take all numbers. Let's clear the screen and let's do it properly again. L is this. Let's ask for the value of L. It is all even numbers from 2 to 100, then all odd numbers from 1 to 101, 1 to 99, and then 101 to 200. Now if I do my take while of or even take while of even L, it will take all elements till they are even and then it will stop. Whereas if I do filter of even of L, it will take all the even numbers till 100 and then there are all odd numbers till 99, and after that there are odd and even numbers alternating. So it will pick out all those even numbers as well. Okay, so this is important. And yeah, I have tried to see how fold L prime works with sums. So yeah, so I think this more or less concludes the demo session for this week. As part of, so please try to explore more on your own, and we will also try to get you work on more exercises. Okay, thank you. Yeah, hope you had an informative session today. Thank you very much.